So recall we stated the Jordan-Hilder theorem last time. Given any finite group G, there exists a composition series. In other words, a subnormal series of this form. So each group is normal in the next group with the property that the pairwise quotients are simple groups. The second part of the Jordan-Hilder theorem is that if you find any other composition series, it must have the same length. So all composition series have the same length. Moreover, up to some permutation, all these quotients are all the quotients in the first composition series are isomorphic to some permutation of the quotients in the second composition series. So the proof of the second part of the theorem relies on two other lemmas that we'll start to go over. One is called the butterfly lemma for reasons that will become clear, and the other one's called the refinement lemma. And both these actually hold for arbitrary groups. The refinement lemma has to do with taking any two subnormal series, and it's some claim that they have some sort of common refinement, which doesn't mean that they have, well, by which I mean they both have some refinement such that the quotients in their refinements satisfy this property. That, of course, requires a definition of refinement. What do I mean by refinement? I mean a refinement of a subnormal series is another subnormal series of this form, say using primes instead, such that gi is equal to g prime j for some j. And every I. Note here, this definition is with respect to a subnormal series, not with respect to a composition series, because, well, you can't refine a composition series. It also implies that this second part to the Jordan-Hilder theorem actually does hold for infinite groups if you can find a finite composition series. That if you find one finite composition series, if the first part of the theorem actually holds for your group, then all other composition series actually have the same length. So let's prove the first part of the theorem. The proof is by induction on G, or the size of the group. And so one case you might consider is that G is a simple group. Or, well, let's not do that. Let's just talk about when G is 1 first. That's the base case. Well, congratulations. There's not much else to talk about. So we're going to assume that G is bigger than 1. Then we'll talk about, well, it could be the case that G is simple. If G is simple, then the only normal subgroup in G is itself. And so then there's your definition. There's your composition series. It's just the trivial one. So if G is not simple, then it must have a non-trivial normal subgroup. There exists n that's normal in G. N's not equal to 1, and n's not equal to G. Well, then n has length smaller than G. So by induction hypothesis, you can find a composition series for n. Likewise, the quotient group has size less than G, and so it also has a composition series. We'll call them G prime 1, G prime 2, etc. up to G prime, say, R, which is equal to G mod N. Well, by one of the isomorphism theorems, here you have to state it pretty carefully, actually. We see G prime R minus 1 is a normal subgroup of G mod N. That means, of course, that there exists some sort of group H. For reasons that will become clear, let's call it H sub R plus K minus 1. That is normal in G. With N normal in it. Such that H R plus K minus 1 mod N is equal to G prime R minus 1. Ignore the K for now. It's there for later because I want to add these terms onto this subnormal series to make it longer. So those are the simple cases right there. This is the harder case. Similarly, as you can guess, G prime R minus 2 is normal in what we're now calling H R plus K minus 1 mod N. So you can construct a group AR plus K minus 2, whose, when you mod out by N, you get G prime R minus 2. And you can keep doing this. There exist these HI subgroups such that HI mod N is equal to G prime R. G prime I. And so note, I had to start at the rightmost and work my way to the left. But you can do that, and so eventually you get all the way down to G prime 1. And so I have H sub K plus 1. And so then I have 1 is normal in G1, is normal in G2, all the way up to N, which is normal in H sub K plus 1, normal in H sub K plus 2, etc. up to HK plus R, which is normal in G. And you can check that each of the pairwise quotients is a simple group, because these ones are simple by induction, because these come from this composition series here. And then these ones are isomorphic to some, well, let's actually point out that isomorphism, because it's worth pointing out that isomorphism. We've got these HK plus I mod H plus K plus I minus 1. You can check by the isomorphism theorems that's equivalent to HK plus I mod N mod HK plus I minus 1 mod N. But that's isomorphic to G prime I mod G prime I minus 1. And those are the quotients from our second normal series, composition series. So using those isomorphism theorems, we managed to take this composition series from the quotient and bootstrap it up to a composition series, or to get the part of the composition series from n to g in such a way that the pairwise quotients were the same. And a confession, this is actually the first time I've ever actually used this isomorphism theorem in an application before. So it's nice to actually use it for once. I mean, it's not the only approach you could have taken. The other approach you could have taken is to let n be a maximal normal subgroup. Which would mean that n is normal in G, and you're assuming that G mod n is simple. So that's claiming, of course, that maximal normal subgroups exist, but one can prove that for finite groups by induction and using the isomorphism theorems, which would hide some of this mess a little bit. So if you could prove such things exist, then you could have just used induction here. And then you're just tacking on an extra term at the end. But why should maximal normal subgroups exist? Well, one would do that proof by induction as well. You would just take an arbitrary subgroup, normal subgroup. If it's not maximal, apply induction. To G mod n, which, not being a simple group, has a maximal normal subgroup by induction. Which we can call, say, H. Then, as you can guess, you can bootstrap to find, well, let's call it H prime. Then there exists an H. That's a normal subgroup of G with H mod n isomorphic to H prime. Then all you have to point out is that G mod H is isomorphic to G mod n mod H mod n, is isomorphic to this G mod n mod H prime. And so by induction, since H prime is maximal normal subgroup in this quotient, this is a simple group. And therefore so is this. And therefore H is a maximal normal subgroup in G. So that'd be one way to avoid this complication and make this a little simpler. And this does describe two different approaches for how to find composition series. This approach just says find a normal subgroup and then keep going to the left and to the right. And this one just says, okay, find a normal subgroup. We'll keep finding a larger normal subgroup till you can't find anything bigger. Make that the largest one, and then keep going down. So here is the butterfly lemma that we need to prove the second Jordan-Hilder theorem. Fix a group G, consider two subgroups, let's call them H1 and H2, and consider two normal subgroups N1 and N2. They're normal inside their corresponding HIs. Then you've got this crazy isomorphism of quotient groups. involving intersections of subgroups and products. So of course we might need to remember product of AB is, AB, A and A, B and B. So there's a lot to unpack. That means that this is a group, this is a group, this is a group, and this is a group. This group is normal in that group. This group is normal in that group. And there's an isomorphism. Of course, there's actually a second step. That's a trade secret. That's part of the butterfly lemma, is that they're both actually isomorphic. To this group. And that's what you actually prove instead. And why would that matter? Because notice the symmetry between 1 and 2. If you permute 1 and 2, this expression becomes that expression. So if I prove one of these and this expression stays the same to some extent. So if I prove one of these isomorphisms, it's equivalent to proving the other one. Note here this vertical line is being used in place of the usual A over B notation we've been using for cosets. Just obviously once they get this big, it's kind of hard to use that notation anymore. Of course, you might ask yourself, why is it called the butterfly lemma? Well, it's got this pretty little history that if you draw the subgroup diagram upside down, so you have the H1 on the bottom and the H2 on the bottom, then we know we've got this normal subgroup somewhere, N1 and N2. And what are these groups? We've got these two different groups. This one is a subgroup of that one. So this one occurs lower in the diagram. Similarly over here, we've got this N2, H1 intersect H2, N2, N1 intersect H2. What other groups do we see in this proof? Well, we see this H1 intersect H2, and we also see this double product thing, which I'm going to draw up here. And finally, of course, there is N1 intersect H2 and N2 intersect H1. And so if I drew this right, it starts to look like a, well, in my case, not so pretty butterfly. But yeah, I didn't draw it right. That's okay though. See, it looks like a butterfly. Hence butterfly lemma. Yeah, it's kind of a nerdy way to do it, but I imagine back in the day when you had to memorize this for a comprehensive exam, having a way to memorize the picture was probably helpful. Alright, so how are we going to prove this theorem? Well, I remember sometimes when I've taught algebra, when I start to prove theorems like this, the first step students always assume is first show everything is normal. But you don't have to do that. The right approach is to, when you're doing isomorphisms between quotient groups, is you need to show at least one of the two sides as normal subgroups so that the quotient is well defined. So we're going to show this group is normal in here, and this group is normal in here. And then we're going to argue that that forces this product to be normal. Therefore, this quotient is well defined. once we do that, then I'm going to actually define a homomorphism from here to here. Prove that it's surjective and prove that this is the kernel. Once you do that, that automatically makes this a normal subgroup for free, because that's just a true fact about kernels of homomorphisms. And then the first isomorphism theorem automatically tells us that this quotient is isomorphic to that quotient. So our first step is to show that when you intersect hi with the other n, I'm going to say not I. It's normal when hi intersect h not I. So, h1 intersect n2 is normal and h1 intersect h2. Let's prove that. So what do I need to show? I need to take something in the left set, something in the right set, and I need to conjugate it. And I need to ask myself, is this still in h1 intersect n2? Well, y and x are both in h1. So certainly y inverse is also in h1 because it's a subgroup. So that's not a problem. X is in n2, y is in h2, n2 is normal in h2, and so again conjugation by y gives you something in n2. So congratulations, we have normality. So there's one of the cases. In the other case, it's the same. Replace the roles of the numbers 1 and 2 everywhere, and you'll see it's the exact same proof. So we now see each of these intersections is normal in this intersection. So let me get rid of my butterfly. Sorry, butterfly. It's flying away off to greener pastures. Why should this product be normal? So what am I pointing out? If H and K are both normal subgroups of some group G, then H times K is also normal in G. That's the fact I want to use here to be able to say that this product is normal here. If I can do that, then I can conclude that H1 intersect N2 times N1 intersect H2 is normal H1 intersect H2. That's our target. So why should this be true? Well, what do things in the product look like? If X is in HK, then it must be able to be factored as little h times little k for some little h in capital H and some little k in capital K. Let me use cursive K so it's a little easier to read. What happens when I conjugate by some element in G? Well, I can always multiply secretly by G inverse G in the middle. And since H is normal, this first factor is in H, and this second factor is in K because K is normal. And so that tells me I can factor this conjugate as an element in H times an element in K. So the conjugate is also in HK. Ergo, the product of subgroups is a normal subgroup. So congratulations, this quotient is well defined. And to make life easier, I'm going to call it D. So D is this bottom subgroup. So now what do I want? I want a homomorphism from N1 times the intersection of the H subgroups to the intersection of the H subgroups mod this normal subgroup I'm now calling D. Well, something in this product is going to look like the form n times little h. Just send it to HD. It's not too hard to see that this map is surjective. I mean, anything over here looks like HD, where H is in this intersection. Well, then just look at phi of 1H, where 1 is the identity element. Likewise, the kernel is going to be those pairs NH with the feature that HD is equal to D, which means that H is in D, which means that H can be factored as A1 or AB, where A is in H1 intersect N2, and B is in N1 intersect H2. It occurs to me sometimes the order matters. If I wrote these two in the other order, then I could actually write the factorization in the order I want, that I need for the proof. So sometimes you have to be careful about order. If I do that in this case, then I actually manage to get H. It's written as a product of something that's already in N1 times something that's in H1 intersect N2. And why do I want to do that? Because that means that the A could have gone with the N to begin with, which means then I'm actually working with an H. That's actually an H1 intersect N2. Instead. And the NA is just an N1, which means that I'm working with N1 times H1 intersect N2. So it's just a clever moving the factor over trick. What is missing? The proof that this is a homomorphism, and actually the proof that it's well defined. One thing that often trips people up is a product just means that every element in this set can be written as a product of elements in these subgroups. It doesn't mean that that factorization is unique. So we need to still check that this homomorphism we just defined is actually well defined. What that means is that suppose I took an element in my domain and I factored it a different way, as an element in N1 and an element in the intersection of the HIs. I need to check that the function I get, the function value is the same for both. So I need phi of NH to be equal to phi of N prime H prime. Or more accurately, I need HD to be equal to H prime D prime. Otherwise, the operation I defined isn't actually well defined, because it depends on the choice of factorization, which would be a problem. But there's really no significant problem, because if I multiply both sides correctly, as so, I get this equality. But these are elements in N1, and these are elements in the intersection of H1 intersect H2. In particular, this tells me that H times H prime inverse is in N1. But it's also in N2, so it's in this intersection. And of course, this intersection of subgroups is actually a subset of D itself. And so when the product of the inverses of the coset representatives lie in your subgroup, then the cosets are equal. Therefore, the function values are the same, and this is well defined. Now we also need to check homomorphism. So take two different elements in my domain, factor it as n times h and n prime times h prime. According to my operations, I should get hd times h prime d, so that should be h prime d. On the other hand, I need to compute this operation, and one way to do it in a clever manner is to sneakily add in an h inverse in the right location, namely right after the n prime. And why would you do such a thing? Because look, now I have a conjugate of n prime by h. And why would I do such a thing? Because because n1 is normal in h1 and h is in h1, so this product right here is in fact in n1, and this product right here is in fact in the product of the hi's. So by definition of my product, I get h prime d. So it is a homomorphism, it's well defined, it's surjective, and its kernel is d. So by the first isomorphism theorem, I have now proven the butterfly lemma. What should be unclear at this point is what this has to do with the Jordan-Hilder theorem. In the next video, when we talk about refining normal series, you'll see one of the ways we can do that is that there's a way to intersect two normal series together. And the approach for intersecting them involves doing constructions like like these things that you're seeing in these numerators and in the denominators in the statement of the butterfly lemma. And so the butterfly lemma is what we use to actually prove the isomorphism, to show that the quotient groups you get from the two refinements are isomorphic.